Hello Year 13. So this is a run through of everything that you need to know knowledge wise for paper 1. So we're going to go through coasts, we're going to go through Earth's life support system, and we're going to go through the skills, the math skills that you need. So starting with coasts. So the first thing that you need to remember is, how do you define a coastal landscape system? For any essay question, for any question that asks you about the coastal landscape system, you need to start with this definition. So you should all know this very well by now. Coastal landscape system is a series of interrelated components or stores and processes or links that form a whole. And we need to remember that we need to talk about how energy and sediment are being stored and are being transferred through the coastal landscape system. Whenever possible, talk about how energy flows through the system. Talk about how sediment moves through the system. So with energy, where does that energy come from that runs the system? So we can talk about kinetic energy, so energy that is where you've got something that's moving. Potential energy, so for example, if you've got a boulder or a piece of rock on the side of a cliff that is hanging by a thread, you've got potential energy, it's ready to drop, it's ready to fall off any time. And you've got thermal energy, which comes from the sun. And this energy then allows the geomorphic processes to shape the landscape. And remember, geomorphic, geo stands for rocks, morphic stands for changing the shape of. So geomorphic are those processes that change the shape of the rocks. So we're talking about erosion, transportation, we're talking about weathering processes for geomorphic processes. So remember that the coastal landscape system is open. Energy and sediment come in and go out. So the inputs include the energy from the wind, the energy that comes from the wind to the waves, the thermal energy that comes from the sun, and the potential energy from the position of the material on the slope. And the sediment comes from erosional processes, comes from weathering processes, and comes from mass movement like landslides. The processes within the system include erosion, transportation, and deposition. And then the outputs are our marine, so sea, and wind, aeolian, erosion. So when the inputs are equal to the outputs, we say that the system, remember, is in a state of equilibrium. But if something happens to disturb this equilibrium, self-regulation takes place in order to restore equilibrium. So if the amount of sediment coming onto the beach is equal to the amount of sediment that leaves the beach in a year, that beach stays the same size. So if you remember, we talk about dynamic equilibrium. During the summer months, the constructive waves build up the beach, and that's because the swash is stronger than the backwash. The swash pushes the material up the beach, the backwash doesn't have enough energy to bring it back down again. And what that does throughout the summer is to build up a steep gradient to the beach. By the time we get to the winter, it's quite hard for the swash to get up the steep gradient, but the backwash is able to whiz back down again. So in the winter, we have winter destructive waves, and this is where the backwash is much stronger than the swash, and it pulls that sand back off the beach again. And so we go round and round in that cycle of self-regulation, maintaining equilibrium in terms of the size of the beach from year to year. So if we were to then look at the movement of sediment along the beach, we know that we need to talk about longshore drift. So the waves come up the beach in the angle of the wind, the swash, and then straight back down due to gravity, the backwash, giving us a zigzag movement of material along the beach. We need to talk about energy being transferred in this process. So the energy comes from the wind. The wind transfers the energy to the waves, and the waves then carry that energy across the ocean. When the wave then breaks, that energy is carried forward along with the water as the wave breaks. and the energy of that wave is then used for erosion or for transportation. So we talk about how that energy flows from the wind to the waves, and then it's used for erosion or transportation. Okay, so we've got to talk about the different influences on the coastal landscape system of different physical processes. So we'll start with the wind. So we know that the wind is the source of energy for erosion as transportation. We've just talked about that. The energy of a wave is dependent on the strength of the wind and the duration of the wind, and also the length of the fetch, the distance to the next nearest landmass. So the longer the fetch, the greater the energy that wave will have. And we know that around the world, wind strength varies and therefore wave height varies. Lots of coastlines have a prevailing wind, most common wind direction. We also have that equation, P equals H squared T. So this tells us that the power of a wave is most dependent on the height of the wave. So wave height is most important in determining how much energy that wave has. So the waves come from the frictional drag of the wind across the ocean. But remember that you've got a forward movement of energy across the ocean, not water. The water molecules are simply going round and round in a circular movement. But as the wave enters the shallow water, if you look at the diagram down the bottom left, the friction of the seabed starts to act on the bottom of the wave. And the trough, the bottom of the wave, slows down. So it's much slower than the top of the wave, the crest. And it gets to a point where you've got instability. The crest is going much faster, so it topples over and breaks onto the shore. And at that point, you've got a significant forward movement of water as well as energy. You've got different forms of waves. Swell waves form out to sea, and storm waves form closer to shore. Storm waves have more energy from the very strong winds that produce them. Okay, we've talked about swash coming up the beach in the direction of the wind and the backwash going back down at right angles due to gravity. And as the wave breaks, the energy of the water takes it up the beach. Once it gets up the beach, it runs out of energy, and it's gravity that brings that wave back down towards the beach, back down towards the sea. The next physical factor is the tides. We don't need to get into a huge amount of detail about what causes the tides. We can mention that it's to do with the moon and the sun's gravitational force and when they're in alignment. We have times of the year where we have very big tides, the spring tides, and where we have very small tides, the neap tides. But more important for coastal processes is to talk about the tidal range. So this is the difference in the height of the water between high tide and low tide. Where you've got a small tidal range, you get a concentration of erosional processes. And this is often what forms the wave-cut notches, which go on to form the shore platforms. Where you've got a high range, so for example the Severn Estuary, or where you've got a funneled landscape, where you've got an inlet and all of that water is squeezed into a small space. So for example, the Severn Estuary has a 14-metre tidal range. You get a scouring effect as all of that water rushes in and pulls back out again twice a day. The next physical factor is geology. When we talk about geology, we need to talk about lithology and structure. Lithology is where we talk about the resistance of the rocks. So where you've got weak lithology, like clay, you will have little resistance to erosion, little resistance to weathering and mass movement, because the bonds between the particles are quite weak. Then you've got, on the other hand, resistant rocks with dense interlocking crystals, and these will be your prominent features in the coastline. These will be the things that stick out or stick up because they've not been able to erode as quickly. And then you can talk about bedding planes. I've put a little link there at the bottom if you want to stop and have a look at somebody talking to you about bedding planes. We've talked about this a few times, so remember, if the bedding planes are horizontal, if the rocks have been laid down in nice horizontal layers, you tend to have vertical cliffs that are very steep. But if the cliffs are landward or seaward dipping in terms of their bedding planes, then you will have a slope that follows the angle of the dip, and they'll be much gentler. Then you can talk about structure. So where you've got faults or joints or cracks, they form weak points that can be easily exploited by the erosional processes. Then you can talk about permeability. So if you've got permeable, porous rocks, they will absorb and store water like chalk. And then you can talk about planform. This is bird's eye view. And we know concordant coastlines is where the same rock type runs all the way along the coast. Discordant coastlines is where you've got alternating bands of different rocks running along the coastline. The other physical factor you can talk about is ocean currents. And although they don't affect the coastal processes themselves, what the ocean currents do is they then affect the climate, which then affects the weathering processes you get in that location. So if you've got a cold climate, you're likely to have freeze-thaw weathering. If you've got a warm climate, you're likely to have chemical weathering. A rip current is where you've got two backwashes combining to create an extra strong backwash, which then pulls the sediment back and creates that triangular shape of sand that we call a cusp. Then we've got to be able to talk about the sources of coastal sediment. So where does the coastal sediment come from? First place it comes from is terrestrial, from the land, and this is from fluvial deposition, so from the rivers. The rivers have picked up all this sediment through erosion, weathering and mass movement that's happened along the course of the river, and the river has carried all that material down to the sea. When the river meets the sea at the mouth, those two bodies of water coming towards each other causes a dissipation of energy, and you've got a low energy environment. And we know that when we have a low energy environment, we get deposition. We also have the process of flocculation. This is where you've got the clay particles, as they come into the salty water from the fresh water of the river, they clump together due to electrical charges, become heavy and sink and are deposited. Then you've got the sediment that comes from weathering. So from freeze-thaw, mechanical weathering, the rain gets into the cracks in the rocks, it freezes, it expands by 9%, then it thaws, then it refreezes the next night, and that process eventually breaks the rocks apart. You've also got the process of salt crystallization, which is where salt from seawater gets into the cracks, the salt crystals grow, and that starts to exert pressure on the rocks. Chemical weathering works better in warmer conditions. Van Hoff's law says a 10-degree increase in temperature will increase the rate of chemical reaction 2.5 times. So it's much stronger, the chemical weathering, in warm, moist climates. Apart from carbonation. Carbonation works better in cold water. And this is where rain and carbon dioxide in the atmosphere combine to form a weak carbonic acid, which then dissolves rocks like limestone. Then you've got biological weathering. This is where tree roots start to break apart the rocks. Mollusks excrete acids, which forms little hollows on the rocks. Then mass movements. This is where you have a large amount of material flowing down the slope at once, a landslide or a landslip. And this is where you've got forces acting on the slope that are greater than the forces keeping the sediment on the slope. So, for example, we've talked about the analogy of the millionaire shortbread, where you've got the solid layer at the bottom and you've got the semi-molten layer of caramel on top of it. And if you were to put it on a slope in the sun, the caramel would slide off the solid layer of shortbread below. Same thing where you've got an impermeable rock with a permeable layer on top of it. That permeable layer becomes saturated and full of water and heavy. It will slide down on top of the impermeable layer below, causing a landslide. We have a rotational slump, where as the material comes down the slope, it rotates round at the bottom. Then we've got sediment that comes from marine erosion. So this is erosion that takes place by the sea. And this is where the waves, their energy, shapes the landscapes. So erosional processes include hydraulic action, which is where the power of the waves, power of the water and the air gets forced into the cracks and joints and breaks the rocks apart. Pounding, again, is where the pressure of the waves literally breaks the rocks apart. Abrasion is where the waves hurl the rocks at the cliffs, where they wear away the rocks like sandpaper, or wear away the cliffs like sandpaper. Solution is where the salts and acids in the seawater that are there naturally dissolve the rocks. Attrition is where two rocks crash into each other and break into smaller pieces. Then you've got aeolian deposition as another form of sediment. So when the winds are stronger than 40 kilometers per hour, the sand will start to roll across the surface. You'll get the process of saltation, where the sand hops along the beach, where it's lifted up and then drops, lifted up and drops, depending on the energy. Sand is relatively heavy, so it's rarely carried in suspension, and it means that any sort of abrasion that's carried out by sand tends to be below 1 meter in height. Once the wind has picked up the sand, and dry sand is easier for it to pick up than wet sand, it's easier, it needs less energy to keep it picked up. And actually attrition is very effective in the wind because there's no film of water around those sand particles. They crash into each other and they break into smaller pieces. Deposition will happen when the friction of the land slows down the energy of the wind and it has to drop that sand because it can no longer keep it picked up. So longshore drift, you've got the diagram there. This is where the swash wave carries the sand up the beach in the angle of the wind. The backwash brings it back down at right angles due to gravity. Zigzag movement along the beach. As this is happening, attrition occurs. So the particles get smaller and more rounded as you go along the beach. If we have a swash-aligned beach, then actually the swash will be coming straight up and the backwash will be going straight down. And in that instance, there will be no longshore drift taking place. The sand simply moves up and back, up and back. Then you've got sediment that comes from offshore and sediment that's deposited offshore. So deposition happens, we know, in the low energy environments of the spits and the lagoons and the estuaries and in the bays. But also during the winter, all of the sand that's pulled off the beach, all of the destructive waves pulling that sand off the beach, need to put that sediment somewhere. And what happens is it puts it just out to sea, forming an offshore bar. And this is where I was saying to you that sometimes in the late summer, people can sort of wade out a little distance and then they can stand on what looks like land again because it's a sandbar that's been created. And then during the summer, that sand will come back onto the beach with the constructive waves. Then you've got the human source of sediment through beach nourishment. This is where we dredge the sand from the bottom of the ocean and pump it onto the beach. The aim being that you create a wide sandy beach that will then absorb the energy of the waves and reduce erosion because you've taken the energy out of those waves. However, as soon as you pump that sand onto the beach, the sand gets moved along through longshore drift. And you have to constantly keep replenishing it. And this is adding an extra input into the sediment budget, which is unnatural, which can cause problems by getting into deltas and infilling estuaries and silting up places that you perhaps wouldn't want it to, like harbours and things like that. Okay, the next section is the influence of flows of energy and materials on geomorphic processes. So, weathering processes, we've talked about physical weathering, we've talked about biological weathering, we've talked about how climate influences the type of weathering. In a cold climate, you get freeze-thaw and carbonation. In a warmer climate, you get chemical weathering. We've talked about mass movements, the rock falls, the landslides, the rotational slides that happen. We've talked about the greater the power and energy of the wave, the greater potential that wave has for erosion. We've talked about the type of geology being important in terms of erosion. Weak lithology means erosion can happen quickly. Resistant lithology means erosion happens slowly. We've talked about fluvial erosion, the amount of sediment that comes down the river, and actually human actions along the river can influence the amount of sediment that comes down. So by building a dam, as we've talked about with the Aswan Dam, the River Nile can stop the sediment coming down from the river. Deforestation can massively impact the amount of sediment coming into a river because you've no longer got the roots of the trees binding the soil together. So it can all be washed down to the coast. We've talked about aeolian erosion. The sediment needs to be small enough to pick it up. And then transportation, depending on the size of the particle, big boulders move by traction, by being rolled along. Smaller pebbles move by saltation, where they bounce along. Suspension is where the sediment's carried along in the flow. And solution is where the sediment's dissolved in the flow. So it depends on the size of the sediment and the amount of energy available, how much movement there will be. And deposition happens when the energy drops and the water is no longer able to keep that particle picked up, and it will drop it. The settling velocity is the velocity or the speed at which sediment of a certain size will be deposited. And obviously the larger particles are deposited first because they need greater energy to move them, and the finer particles will be carried furthest before they are deposited. Right, so now we've got our distinctive landforms that we need to talk about. So firstly, our landforms that are formed by erosion. So headlands and bays. So headlands and bays form along discordant coasts where you've got alternating bands of weak and strong lithology. The weaker bands of rock erode much faster to form bays, whereas the resistant bands remain sticking out into sea as headlands. The width of the bay is determined by the width of the band of weak rock. Then we need to turn it into an A-level answer. We need to talk about wave refraction. So wave refraction slows the waves in the shallow water off the headlands and moves faster into the bays. What we end up having is the waves refracting. The waves are converging on the headlands and concentrating their energy on the headlands. And then in the bays, the waves are, the orthogonals are dissipating. They're diverging, which takes away the energy and allows us to have a nice low energy environment for a beach to form in the bay. Cliffs. Cliffs will vary in their profile depending on the geology. If you've got horizontally bedded plains, then you'll have very steep cliffs. If you've got landward dipping or seaward dipping, they follow that pathway and they're much gentler. Undercutting is where the waves attack the bottom of a cliff and cut out the bottom, leaving the top unsupported, and as a result you get that falling down and the cliff moves back over time and becomes higher. Shore platforms. So these occur when destructive waves break repeatedly on a relatively steep cliff. So it's where you've got a small tidal range and you get a concentration of wave energy. That continues until it cuts a wave cut notch, continues to undercut the rock above, and so eventually the rock above collapses down. And what it leaves is a platform of rock at the bottom. That platform will never get wider than 500 meters because the friction of the platform will mean the waves never get to the base of the cliffs and never get to erode it any further. But weathering processes will then start to act on the platform. So if it's a cold environment, you'll have freeze-thaw weathering. If it's warmer, you'll get salt crystallization. The rocks get dragged across the platform and they dissect the rocks and cause big scratches. Where the boulders are too big to be removed by the waves, they accumulate, they build up on the platform. And you've got mollusks secreting acids that are creating small hollows in the rock as well. And it's important you talk about those processes, those weathering processes, as important as the erosional processes in terms of shaping this shore platform. Geos. So geos are narrow, steep-sided inlets, and you've got a picture there at the bottom left to have a look at one. Even a resistant headland has a weakness, has a joint or a fault, and that joint can be exploited by hydraulic action, abrasion, solution, and taken out over time to leave a steep-sided inlet. So one example is Huntsman's Leap in Pembrokeshire. It's 35 metres deep, and that was eroded along a large joint in limestone. Sometimes they form where you've got a tunnel-like cave and the roof collapses down. Sometimes it's only a partial collapse, like you've got in the diagram at the bottom right, and you end up with a blowhole. So you've got a narrow inlet, but you can't necessarily see the sea at the bottom. But the sea can get up when you've got a really big storm, and water can shoot out the top of that blowhole with lots of force and lots of white water. Hydraulic action is particularly important in forming geos. Abrasion is also important, but they may also be associated with old mining shafts. Okay, then caves, arches, stacks and stumps. So due to that wave refraction, energy is concentrated on a headland. Any weak points, like joints or faults, will be exploited by the erosional processes of the sea to form a cave. Wave erosion continues until the cave erodes right through to form an arch. Now the arch is above marine processes, apart from the tides, wetting and drying. So it's now weathering processes that act on the arch. So freeze-thaw, salt crystallization, depending on the climate. You've got seaweed, you've got seabirds, you've got mollusks. And eventually, the top of the arch will collapse down, leaving a stack. The stack is eroded at the bottom and eventually falls down to leave a stump. And an example is Old Harry and his wives along the Foreland headland in Swanage in Dorset. So now we're moving on to our landforms of deposition. So beaches. Beaches form when we have constructive waves. Constructive waves push the sand up the beach because the swash is much stronger than the backwash. The backwash can't bring the sand back down again. Sandy beaches tend to be gentler gradients, and that's because the sand becomes very compact when it's wet, so you don't get much in the way of percolation. So the swash comes up and pretty much the same amount of water goes back down again with the backwash. A shingle beach is much steeper. This is because the swash wave goes up, but then the water percolates down through the shingle and very little water makes its way back down as backwash. So all of the shingle is pushed up the beach, making it really steep. Then we talked about the fact that you have some beaches that are drift aligned, and this is where they have longshore drift. Swash aligned beaches is where the swash goes straight up at right angles and back down again at right angles. The beach will have different profiles depending on whether it's summer or winter and where it is in that process of dynamic equilibrium in terms of the constructive or destructive waves. Then we've got our spits. So spits are long, narrow beaches of sediment that are attached to the land at one end and extend out across a bay or an estuary. So these occur when there is a corner in the coastline. Longshore drift does not turn the corner, but continues to deposit sediment out to sea, where that sediment builds up above the level of water and becomes consolidated land. The end of the spit gets hooked round by the secondary wind and waves and through the flow of the river, stopping the sediment getting any further way across. In the shelter of the spit, you get low energy, so you get salt marsh and you get a lagoon forming there. Now we need to also be able to say that spits are dynamic. They only exist as long as deposition is greater than erosion. A big storm overnight can remove a large amount of sediment from a spit and change its shape dramatically. They are also very low-lying, and so they're vulnerable to sea level and being inundated and being cut off by the rising sea level. An onshore bar is where a spit grows across from one bit of the headland to another bit of the headland and joins one bit of the mainland to another. And you get a lagoon forming behind the bar, like you can see there in that photograph. They're also very dynamic, and they also only exist as long as deposition is greater than erosion. They will also have a large amount of sediment removed by a big storm, and they are also vulnerable to sea level rise. They form in a very similar way to spits in terms of longshore drift. Tombolos is where the beach connects the mainland to an island, like in that picture there. And this is where the spit continues to grow out to sea until it joins to the island. And an example is Chesil Beach. They only form when the sediment load exceeds the tidal current, and again they are only there as long as deposition is greater than erosion. A big storm will remove a lot of the material, and they are vulnerable to sea level rise. Salt marshes form in low energy environments, so for example in an estuary or on the inside sheltered part of a spit. And these are vegetated areas of deposited silt and clays. A salt marsh is inundated by the tides twice a day as the tide rises and falls. So you need salt tolerant plants like eelgrass and spartina. And these plants grow initially, and their roots and their leaves then trap the sediment. And that sediment then builds up over time as the tide comes in and out, which increases the height of the salt marsh. The higher up the marsh you go, so the further towards the land, the greater the vegetation. And this is because the higher part of the marsh is not inundated by the sea for anywhere near as long as the lower part of the marsh. High tide only gets there for an hour a day, or maybe 2, and the bottom of the marsh is often underwater. So therefore, very few plants survive at the bottom. Many more plants are able to survive 2 hours of inundation a day. You also have a series of creeks that drain the marsh. So you get these depressions full of salty water. Nothing grows in those depressions because it's too salty for any vegetation to grow. Okay, the next section is to look at how climate changes the coastal landscape. So first of all, thinking about sea levels falling. Sea levels falling during glacial periods. So 25,000 years ago was the end of the warm glacial period. Temperatures were 9 degrees colder than today, and the sea level was 90 meters lower. Since then, temperatures have increased and sea levels have risen, and that period of sea level rise that we're still in now is known as the Flandrian transgression. Changes in the height of sea level are called eustatic changes, and they're influenced by mean global temperature and the amount of ice that's melting and the amount of thermal expansion that's taking place in the oceans. So during glacial periods, sea levels fall, and during interglacial periods, sea levels rise. Isostatic changes are to do with changes in the height of the land. So Scotland, for example, is still rebounding from the last time it had an ice sheet on top of it. The ice sheet was so heavy that it compressed the land down, and the land is still rebounding and still rising back up to its original place. So here, sea level rise is relative. Physical factors that affect climate and therefore the volume of water in the ocean, remember from GCSE, include Milankovitch cycles, sunspots and volcanic eruptions. So as global temperatures decrease in a glacial period, more precipitation falls as snow. This turns to ice, and so the water is stored on the land as ice rather than in the ocean as liquid. Therefore, sea levels fall. Also, as temperatures decrease, the water molecules themselves contract and decrease in density. And so this is the opposite of thermal expansion. This is thermal contraction. So a 1 degree rise in temperature will lead to a 2 metre decrease in sea level. Okay, so as sea levels fall during glacial periods, what happens is we get relics of the former coastlines that were once at sea level. So a raised beach is a former shore platform that used to be at sea level but is now inland, is now higher up because the sea level has fallen away. Sometimes you even find caves, arches, stacks and stumps some way inland where you've got a raised beach that used to be at the shoreline. So for example, the southern tip of the Isle of Portland near Weymouth in Dorset is a distinct raised beach. It's 15 metres above present day sea level, and it formed 125,000 years ago when sea levels were much higher than they are today during an interglacial. Marine terraces are similar. This is where you've got formerly submerged land that has now been exposed, either because the land is uplifted or because the sea level has lowered. You've also got abandoned cliffs. So these are cliffs that were once being eroded by the sea because they were down at sea level, but are now inland and no longer being affected by marine erosional processes. However, they are still being shaped by weathering processes. We've got Hadley's abandoned cliffs, abandoned 10,000 years ago and 50 metres smaller than it was at that time due to weathering. These landforms, these emergent landforms from sea levels falling, it's really important to recognise that they are still being shaped. They are still being shaped by weathering and mass movement, no longer being shaped by the sea and wave processes. On the top of the abandoned cliff in Portland, you've got frost shattering taking place. You've got freeze thaw taking place. And it's also important to recognise that a lot of these landforms inland are very difficult to recognise. They're certainly not major landforms that people can see, that people will come to visit. They've been covered in vegetation, which makes it very difficult to actually see them. Once again, if sea levels rise, these landforms will come back to the coastline and will once again be shaped by marine processes at some point in the future. Then you've got your submergent landforms, and these happen when sea levels rise during interglacial periods. So as temperatures rise, the ice from the ice sheets, the ice caps, the glaciers melts. That increases the volume of water in the oceans. We also have thermal expansion. As the water molecules warm, they expand and increase in volume. So a 1 degree rise in global temperature will lead to a 2 metre rise in sea level. So the first submergent landform we need to be able to talk about is a ria. A ria is a submerged river valley, and they form as sea levels rise and they flood that former river valley. They have a distinctive V shape under the water. The depth gets progressively deeper towards the centre, with exposed valley sides either side. And that is reflective of the former V-shaped valley that was formed by the river. In long profile, they've got a smooth profile with uniform depth, but in plan view, you can see that they wind around following the original meanders of the river. You've got some of these rias along the Devon and Cornwall coast that formed during the post-glacial sea level rise of the Flandrian transgression. During the interglacials, there's further deposition because the rivers have less energy. Then you've got the fjords. The fjords are the submerged glacial valleys, and these are U-shaped with uniform water across the fjord. Some of them are huge. So the Sonje Fjord in Norway is 200 kilometres long. Those in Scotland are less well developed because the ice was not as thick there during the last glacial. They all have a shallower section at the end due to the lower rates of erosion and thinner ice. During the Flandrian transgression, you've had a lot of marine erosion and some fjords have got deeper. But you've also got a lot of meltwater coming down from the melting glaciers, bringing sediment and depositing it into the fjords. Then you've got shingle beaches. So as sea levels rise, the water brings shingle that's been deposited offshore up onto the land. So it's like new land emerging from the sea. And some people think that Chesil Beach, the Tombolo, formed in this way. Sediment carried into the English Channel by meltwater during the Worm Glacial was carried onshore by the waves. And it's also important to talk about these weirs and fjords being modified. They were formed by rising sea levels, but they continue to be shaped by subaerial weathering processes. Sea levels predicted to rise 0.6 metres in the next 100 years, so the level of water will rise in the weirs and fjords. More storms, larger waves will increase the erosion. And shingle beaches are especially vulnerable to modification because they're made up of unconsolidated material. So Chesil Beach could be massively impacted by rising sea levels and longshore drift. Okay, so then we get to our case studies. We've got 3 case studies we need to know. The first one is a case study of a high energy coastline. And this is going to be Saltburn to Flamborough Head in Yorkshire in England. So we need to know the physical factors that influence the formation of the landforms along this coastline. We need to be able to talk about the interrelationship of the landforms and how the landscape system has changed over time. So this is a high energy coastline. There is a large fetch of more than 500 kilometres, which gives us high energy waves. It's a 60-kilometre stretch of coastline, and there are differences in lithology, in rock resistance. And what this gives us is it gives us headland and bay sequences due to differential erosion, due to the differences in wave energy in terms of the waves being dissipated with the orthogonals. The north-facing part of the coastline is most exposed and so therefore has the greatest energy and the biggest rates of erosion. Robin Hood's Bay is an example of a bay that's been eroded into the relatively weak shale. Either side you've got resistant bands of sandstone that have formed the headlands of Ravenscar and Ness Point. Another bay is called Filey Bay, which has been eroded into the weak Kimmeridge clay. And again, you've got resistant limestone and chalk either side. Erosion varies depending on how strong the rock is, from 0.8 metres per year for the clays to just 0.1 metre a year for the more resistant rocks. So we have differential erosion. The steeper slopes are found where you've got the resistant sandstone and limestones, and the gentler slopes where the weaker clays and shales are found. Wave refraction has concentrated the wave energy onto the resistant headlands, and the weak points have then been exploited. So, for example, a major joint in the chalk at Flamborough Head has been exploited to form Selwick Bay. Further weak points have been exploited to form caves, and then arches, and then later stacks. So, for example, Green Stacks Pinnacle. There are more than 50 geos that are formed along this coastline, with the majority aligned facing the dominant wind direction of northeast, northeast-east. And blowholes have also developed where the chalk and clay have collapsed into the sea, creating that sort of funnel effect. To the north of Selwick Bay, several blowholes have merged together to form a complex inlet. In the low energy bays like Filey Bay, beaches are formed. There's not really much input from rivers along this coastline, and the high energy waves remove the sediment before it can accumulate, so therefore the beaches grow very slowly. With high energy, longshore drift is significant. You've got lots of energy for that movement to take place, and it takes place from north to south. Where you've got headlands, the longshore drift is interrupted, and then the sediment builds up to therefore form the beaches. There are no spits because of the high tidal range and the lack of estuary. High energy waves have also formed shore platforms, like in Robin Hood's Bay, and we've got some of the biggest relics of past interglacials. In recent years, there's been a net increase in sediment, and winter storms have continued to have a big erosional impact along this coastline. And there's just a diagram, if it helps you to draw it out as a diagram and to label the different landforms along the headlands. Then we've got our case study of a low energy coastline, and this is the Nile Delta in Egypt. And again, we've got to look at the physical factors, the interrelationships, and so on. So here we've got a low energy coastline, so deposition is going to dominate. And actually, we've got huge rates of deposition that have taken place over time along the Nile Delta to build up this delta. The River Nile is the longest in the world, flows across Central Africa. It doesn't have a huge discharge, but it carries a huge sediment load, the River Nile, 4.26 tonnes per hectare per year. So deposition in this low energy environment has built this huge delta that starts 160 kilometres inland at Cairo and fans out to the sea. There are three distinct zones: the foreshore plain, the frontal plain, and the sandy zone. The foreshore consists of ridges alternating with lagoons and salt marshes. Now, the humans have built the Aswan Dam in 1964 in order to control the flow of water. But the dam has effectively stopped the sediment supply to the delta. It stopped the sediment being fed in to continue to build up the delta. As a result, erosion has increased to 48 metres per year, leading to significant changes along the shoreline. Before, 120 million tonnes of sediment was deposited every year. Now it is trace. Sea levels are also rising 1.2 millimetres per year, and this has led to larger waves, greater energy, increased erosion. The prevailing northwesterly winds have led to a constant easterly movement of waves and sediment. The coast is tideless. We don't have any tides. Therefore, underwater sandbars have built up. And there are long crescentic bar systems associated with rip currents and a lack of longshore drift to the west of Abu Quir Headland, whereas to the east of Abu Quir Headland, we've got a dominant easterly movement of longshore drift, creating parallel bars. And these bars, crescentic or parallel, have cut off segments of the Mediterranean Sea to form lagoons. And there's just another diagram that puts all of the Nile Delta onto one big page, locating them on there. Finally, we need a case study of one coastal landscape that's being managed. And our example is sandbanks in Dorset. And we need to be able to talk about intentional and unintentional impacts of what humans have done. So this is a 1 kilometre peninsula. The hook end, as you can see in that picture there, is extremely high land value, the 4th most expensive in the world per square metre. A management strategy was required to protect the coastline from erosion and flooding, as the sea level is predicted to rise 0.6 metres in the next 100 years. You've got significant high value properties. You've got a blue flag beach that has a gentle wide slope and is a major tourist attraction. And if the peninsula itself was to be breached, was to be overtopped by the water, it would not be possible to simply drive across to the peninsula. At its lowest point, the peninsula is just 2 metres above sea level, so it's threatened by breaching in the near future if we were not to do any sort of management. The pool harbour itself is also really high value. You can just see all of the little yachts there that are moored there, and that's also really important. If they were to do no management, they estimate there'd be £18 million worth of damage in the next 20 years. So the management strategy was to build rock groins to stop the sediment moving along the beach and to build up a deep, wide, sandy beach. The intention being to absorb the energy of the waves and therefore reduce erosion, which is currently 1.6 metres per year. It would also stop the sediment accumulating in the harbour entrance, keeping access free for the ships. They're also going to carry out beach nourishment, which is where they dredge the sand from offshore and dump it onto the beach, costing £20 per metres cubed. Again, the intention is to absorb the energy and protect against erosion. And dredging from the harbour also helps to keep it free of sediment. The consequence of the management strategy, it's been extremely successful in holding the line and stopping any further erosion. In fact, it's been so successful that unintentionally they've actually managed to increase the width of the beach, which makes it even more attractive to tourists and even more protecting against erosion going forward. So that's the end of the coasts content. And then remember, you also need to be aware that you're going to have to do some maths questions. So you need to be able to do the mean, the median, the mode, the range, the interquartile range, and standard deviation. So can you calculate the median value? This is where you put the values into order and you find the middle one. Can you find the range? This is where you take the highest value and minus the lowest value from that. Can you calculate standard deviation? Remember, there is a very specific way that you need to do this. So, first of all, you calculate the mean. Then you find the difference between the mean and each of your values. Then you square each of those difference values and add up all of those squared values. Then you divide that number by the number of values, and finally you square root your answer to give an answer to 2 decimal places. You have to be able to show all of that working to get the 4 marks that will be available for it. You also might be asked to describe the distribution of sediment on these kind of distribution graphs. So to be able to talk about a bimodal graph on the left, to be able to talk about a negatively skewed graph on the right. Okay, so now we've got our Earth's life support systems section. So the first thing that we need to be able to talk about is the water cycle. We need to know that the water cycle is a system. It's a system with stores and flows that are joining it all together. On a global scale, the water cycle is a closed system. So no new water is created or destroyed. The same amount of water simply cycles round and round the water cycle. And the cycle itself is driven by the energy from the sun. Only energy, not water, crosses the boundary. On a smaller scale, one drainage basin, so the area around one river, is an open system. Water enters and water leaves. So the inputs are the precipitation, channel precipitation. The flows are stem flow, surface runoff, infiltration, through flow, percolation, groundwater flow, ablation. And the outputs are as the water flows into the sea and evaporation. So we need to be able to talk about the distribution and size of the major stores in the water cycle. So the biggest store is the ocean. It's by far the biggest store. You could look at learning the value, the kilometres cubed if you want to. We also need to be able to talk about the fact that 97% of the Earth's water is saline, is salty. And we also need to be able to talk about the residence time. So water molecule in the ocean will be there for an average 3,600 years. Ice is the second biggest store. Residence time there, though, is much longer, 15,000 years. The atmosphere is a relatively small store, only 12.7 thousand kilometres cubed. However, the flows into and out of the atmosphere are really fast. So precipitation, evaporation, coming in and out, the average residence time is only 9 days. Less than 10 countries hold 60% of the world's available fresh water. Fresh water is a tiny proportion of the water that's held in store. 3/4 of it is actually frozen in the ice caps. In general, as you move from the equator to the poles, there's a decrease in the amount of water vapour in the atmosphere. The biggest concentration of water vapour in the atmosphere is near the equator, and the least is at the poles. The characteristics of the main inputs and outputs. So we've got precipitation. This is where water and ice falls from the clouds to the ground. So water vapour rises in the atmosphere. It cools to dew point where condensation occurs, and it changes state from gas to liquid. The water droplets aggregate together until they reach a critical size, and they fall then from the cloudless precipitation. And you could name drop the collision theory or the Bergeron-Feindeisen theory. The type of precipitation will vary depending on the latitude and how hot or cold it is, or the season. Ablation is snow melt, and this is really important for certain parts of the world like Canada and America in particular, whereby the snow builds up over several months of the winter, and then in the spring it all melts at the same time and all makes its way into the rivers. So snow is a really important store of water in the cold season. 75% of the Western USA's water comes from snowmelt. It's an important source of fresh water for them. Evapotranspiration combines evaporation, which is where the sun heats up the water and the water changes state from liquid to gas, and transpiration, which is where diffusion of water vapour into the atmosphere takes place from the stomata on the leaves. And this is responsible for about 10% of moisture in the atmosphere, influenced by the temperature, the wind speed, and the amount of water available. So this is just an overview of the water cycle. So we start with the water in the ocean, and the sun is heating up the water, and that is causing the water liquid droplets to change state into water vapour gas. That water vapour rises. As it rises, it cools down, and it cools down until it reaches dew point, which is where the air is saturated. You can talk about the environmental lapse rate, which is where the temperature cools 6.5 degrees per kilometre up you go. As the air rises and cools, it also expands, and we get the process of condensation taking place. And this is where the water vapour turns back into water liquid droplets. And condensation occurs where the clouds form. Clouds are visible aggregates of water or ice that are floating in free air. Within those clouds, the water droplets aggregate and they collide together. You can talk about the Bergeron-Feindeisen process until they reach a critical mass, at which point they fall from the cloud as rain, hail, sleet or snow, depending on the temperature of the lower atmosphere. When the rain falls, if there is vegetation, if there are trees, then there will be interception. Now it depends on the type of vegetation, how much rainfall will be intercepted. So a coniferous tree intercepts far more than a deciduous tree because of the needles, because of the triangular shape is very efficient at collecting and catching water. Interception also varies seasonally. So in the winter, when there are no leaves on the trees in this country, you get very little interception. In the summer, when the leaves are all over the trees, you get much more interception. If you've got a surface that is already saturated, then the interception is going to be very low because it's already full of water. You also get the processes of through flow and stem flow. So through flow is where the water lands on a leaf, but there's so much water landing on that leaf it gets too heavy for the leaf to handle, and the leaf drops all of the water and it falls to the ground. That's through flow. Stem flow is where the water literally flows down the stem of the plant or the tree to the ground. If we've got a permeable surface, we will have infiltration, where the water soaks into the soil layer. We will also have percolation, which is where the water soaks down into the deeper rock layer. Now, the movement of water through the soil layer, the top surface layer, is called through flow, down into the streams and rivers. And then deep down in the rocks, you've got groundwater flow, which is incredibly slow, can take hundreds of years, and that water eventually emerges as springs. Really important for keeping the flow of rivers going when it hasn't rained for a long period. So an important source of recharge for the rivers. Okay, so then talking about carbon. So we talk about carbon as being the building block for life. So it's got a simple atomic structure. It's able to bond with other atoms of carbon and other elements to create complex molecules. And these form the basis of all living matter: proteins, sugars, carbohydrates, fats. So the biosphere is built on large molecules of carbon atoms. All of our agriculture, all of our crops, all of our trees, all of that is important for humans. So we use those kind of things for food, for timber, for paper. Carbon is also an economic resource, particularly through fossil fuels, so coal and oil, which power the global economy. Oil is also used to manufacture plastics, paints, synthetic fabrics. So it's incredibly important for us as humans. There we've got the basic carbon cycle. So we've got carbon flowing in and out of the atmosphere store. Carbon flows from the atmosphere to plants through the process of photosynthesis. Carbon returns to the atmosphere through respiration, either by the plants or by the animals that have eaten the plants. The plants and animals will die and they will decompose, and the decomposers, the fungi, will respire as they are breaking down that material, and that puts carbon back into the atmosphere again. Then we've got the oceans and the atmosphere. So the carbon moves from the atmosphere to the oceans, or vice versa, by the process of diffusion, from higher concentration to lower concentration. The plants and the sea life within the oceans absorb and use that carbon. It forms their shells and their skeletons. When they die, that then falls to the bottom of the ocean, builds up in layers, and sedimentation turns it into rock, limestone and shells. That's the calcium carbonate that's come from their skeletons and their shells. And then you've got fossil fuels. So fossil fuels are found in the rocks beneath the ocean. Those fossil fuels are used by humans and burnt, and that puts carbon into the atmosphere. That's our human added section to the carbon cycle. Naturally, those fossil fuels would be released in terms of combustion by a volcano. So the rocks in the seabed, when they reach a subduction zone through seafloor spreading, would eventually release the carbon into the atmosphere, but that can take thousands and thousands of years. And humans are going in and taking those fossil fuels out where they should be stored for thousands and thousands of years, and burning them and releasing that carbon into the atmosphere, where we are throwing this system into disequilibrium by adding that extra flow into the atmosphere. So we need to be able to talk about the distribution and size of the stores of carbon. So the rocks, the carbonate rocks, are the biggest store of carbon. So we're talking about rocks like limestone and chalk. Second biggest store is the oceans. and it's the cold polar winds that absorb most carbon from the air. The warm equatorial waters have a lower diffusion rate, but we have got a movement of that carbon upwelling at the equator, downwelling at the poles, moving through the oceans. The atmosphere is a relatively small store of carbon, but it is crucial, and it represents most of the carbon in circulation at any one time through the process of photosynthesis and respiration in and out of the atmosphere. It varies throughout the year, it varies around the world. The northern hemisphere has the highest concentrations of carbon in the atmosphere around the major emission sources. But they don't just stay over the country that's producing the sources of carbon. The winds obviously blow that carbon all around the world. Seasonally, when we've got the leaves on the trees during the summer, much more carbon is taken in through the process of photosynthesis, and as a result there's far less carbon in the atmosphere in the summer. In the winter, when there's no leaves on the trees, there's far less photosynthesis happening, and as a result there's far more carbon in the atmosphere. In the southern hemisphere, the large fluxes entering the atmosphere tend to be when they have big forest fires, because it's not as industrial in the southern hemisphere. On the land, carbon is stored in organic matter, both above and below the ground. Most of it's in the tropical rainforest and the boreal forests. 86% of the world's above ground carbon is found in those forests. The deserts, the tundra are very poor stores of carbon due to the lack of vegetation. Okay, then we need the characteristics and main inputs and outputs of the carbon cycle. So we can talk about precipitation. So the rain has carbon from the atmosphere dissolved within it that forms a weak carbonic acid. We've got more carbon in the atmosphere due to our emissions that we're creating, so rainfall is becoming more acidic. That rainfall makes its way into the oceans, which makes the oceans more acidic and causes all kinds of issues of acidification. Then we've got photosynthesis. So the plants on the land, and remember the phytoplankton in the oceans, use the sun's energy, carbon dioxide from the atmosphere and water, to convert light energy to chemical energy. And they use that to grow, reproduce and release carbon back through respiration. Decomposition. So the decomposer organisms, the bacteria, the fungi, break down the dead organic matter. They extract the energy and they release carbon dioxide into the atmosphere as they respire. The rate of decomposition varies around the world, so it's much faster where it's warm and humid and much slower when it's cold and dry. Respiration is the opposite of photosynthesis. So this is where carbohydrates are fixed from photosynthesis, are now converted to carbon dioxide and water. And carbon flows in and out of the atmosphere through those two processes of photosynthesis and respiration. Combustion is where organic matter burns in the presence of oxygen and it releases carbon dioxide. And naturally, we get combustion when we get wildfires in places like Greece and California, caused by lightning when you've got a very, very dry area of land. And actually, these forest fires, these wildfires, are important for the natural carbon cycle. We get a log jam, we get a build-up of fallen leaves throughout the autumn, and all of the carbon is locked away in those leaves. The fires burn the leaves and release the carbon into the atmosphere and make the soil nice and fertile for the next year's growth. However, we are seeing more forest fires with warming climates, and actually we're getting to the point now where the equilibrium of that process is being tipped and more carbon is being released into the atmosphere than used to be. And then of course we've got burning fossil fuels. We burn them for energy, and so we're releasing carbon from what should be a very long-term geological store into the atmosphere. And that carbon, remember, doesn't stay in the atmosphere. Some of it will diffuse into the oceans. So we end up with much more carbon, not only in the atmosphere causing problems, but also in the oceans causing problems. Then you've got weathering. So this is the in situ, where it is, breakdown of rocks at the Earth's surface. So you've got carbonation, where the rainwater contains weak carbonic acid, and carbonation slowly dissolves the limestone and chalks and releases the carbon from the rocks into the river and then into the ocean and then into the atmosphere. Weathering's more effective where you've got soil covering the rocks, because the soil adds to the acidity. And actually this chemical weathering transfers 0.3 billion tonnes of carbon into the atmosphere and oceans every year. So this just looks at the overall carbon cycle in just a little bit more detail. So again, start in the middle, you've got those flows of photosynthesis and respiration between the atmosphere and the biosphere, the plants and animals. You've got the movement from the plants to the animals when they eat the plants. You've got a little asterisk there to say that photosynthesis varies diurnally. So during the day, you've got a flow from the atmosphere to the vegetation via photosynthesis. At night, it's reversed because there's no sun, so no photosynthesis. You've got the diffusion from the atmosphere into the oceans, and you've got a little bit more detail there about carbon sequestration. So this is where carbon is taken in and stored. So within the oceans, you've got the physical pump and the biological pump taking carbon in and moving it around the ocean. So the physical pump is where diffusion brings the carbon into the surface water, and you get that movement of water through the oceans where you've got cold water sinking or down dwelling at the poles, carrying the carbon down to the depths, where it gets carried along by the currents and eventually upwells at the equator, where it can then diffuse back into the atmosphere again. And so you've got that movement around the oceans. Then you've got the biological pump. This is where the carbon is taken in by the phytoplankton through photosynthesis. Then the marine life eats the phytoplankton and the carbon passes through the food chain until the marine animals die and their shells and skeletons sink to the bottom of the floor and accumulate, where that carbon is stored within the rocks itself, in the limestone. And then you've also on the other side got the combustion that we've talked about and the fossil fuels. So you need to be able to talk about the case study of the Arctic tundra, and you need to be able to talk about the water cycle and the carbon cycle specifically in the Arctic tundra. So where is it? It's northern Canada, Alaska, Siberia. And remember, it's everything north of the 10 degrees C July isotherm. So anywhere that doesn't get up to 10 degrees in the middle of summer in July. So everywhere north of that never reaches 10 degrees. It's colder than that even in the middle of summer. And that's also known as the tree line, because trees don't grow any further north than that because it's too cold for them to grow. So the water cycle, specifically in the Arctic, we need to be able to talk about the fact that it's very low precipitation because it's high pressure and most of it falls as snow. There's very little moisture in the atmosphere because you've got very low temperatures, so very little humidity. Very little evapotranspiration because there's very little vegetation, certainly no trees, and a very short growing season in the summer. Very little evaporation because all of the sun's energy is used up melting snow. Certainly no convection because the air is not being warmed by the land and rising. All of the water on the surface and in the soil is frozen. It becomes an impermeable surface, and so the water can't infiltrate and sits therefore on the surface. So there's no percolation, no groundwater flow, everything's frozen. Seasonally, in the winter we get a big accumulation of snow and ice, and then in the summer that snow and ice melts and the top metre of permafrost thaws out, which gives us a big increase in the amount of flowing water, a big increase in the water in the rivers and ponds and lakes, but all of it stays on the surface because the rest of the ground is frozen and it can't sink away, it can't soak away. So it becomes a temporary store of water on the surface. The carbon cycle. We know that the permafrost is a huge carbon sink. So when you do have the short summer season and the plants grow, then they die and everything freezes. And all of that dead and decaying plant matter is frozen in a big freezer. And that locks away all of the carbon in the tundra permafrost, in the tundra soils. So the amount of carbon in the soil in the tundra is 5 times greater than the amount in its vegetation. Seasonally, we've talked about the summer, the active top layer of permafrost melts and you do get some plants growing very rapidly because, remember, you've got 24 hours a day of sunlight. And so those plants can photosynthesize for 24 hours a day. They then die and decompose, and that does release carbon through respiration. In the winter, you do get some pockets of unfrozen water because the snow insulates some areas and allows some slow decomposition to take place beneath it. In the past, the permafrost has been a carbon sink. It's taken in more carbon than it's given out. Today, we're a bit worried that we've passed a tipping point and it's actually become a carbon source. It's giving out more carbon than it's taking in with all the melting permafrost. However, we also know that there is this long-term feedback mechanism that could occur whereby more CO2 in the atmosphere will increase the amount of plant growth. And with the increased amount of plant growth, those extra plants will take in more carbon dioxide, and it's possible that we could restore equilibrium to the carbon budget through that process. Okay, we need to be able to talk about physical factors that affect the flows and stores in the water cycle and then in the carbon cycle. So physical factors include temperature. 8 or 9 months of the year there's a negative heat balance. Average monthly temperatures are below freezing, so the ground is permanently frozen. Only that top metre or so thaws in the short summer season. So that makes the ground impermeable for most of the year. In the summer, when that top layer thaws, water then sits on the surface. It's not able to infiltrate because it's impermeable. Another physical factor is the relief, the shape of the land. It's very flat. There's minimal relief because there's been so much erosion and weathering over the years. So the water doesn't flow downhill, but tends to sit on the surface, which leads to waterlogging. We also have chaotic glacial deposits that have been put down, which change and obstruct the drainage there. In terms of the carbon cycle, temperature means little vegetation grows because it's too cold, which means there's little carbon in the biomass and very slow decomposition. And so the frozen permafrost is a big store of carbon, and when it thaws, that carbon is released. The organic matter in the soil is another physical factor. It's the largest proportion of organic matter found in the soil in the world. So it's essentially frozen, like a freezer. Very slow decomposition, so that soil stores a huge amount more carbon than the vegetation. And then you've got the mineral composition of the rocks. So they tend to be frozen. You get a huge amount of freeze-thaw occurring. You get cryoturbation, which is where you get thawing and freezing, which mixes around the rock fragments that have been left by the glaciers and forms the soil. We also need to be able to talk about the impact of the oil and gas industry on the water and carbon cycles. So in Alaska, we've got a vast wilderness of tundra, which is really important environmentally and ecologically. Oil and gas were discovered there in 1968 at a place called Prudhoe Bay. It's very difficult to get that oil and gas out, to extract it, because it's such a harsh environment and it's such a remote location. But it's had big impacts, this industry, on the carbon cycle. And it's all to do with the permafrost thawing. We put settlements in, infrastructure in, which diffuses heat, which causes the permafrost to thaw out. We create dust, which makes the snow dark, so it absorbs the heat rather than reflects the sun's rays. We chop down vegetation, which would have insulated the permafrost. And then all of that extra melting permafrost releases carbon and methane. We also have those gas flares and places like that where they're looking to see if the gas is actually being extracted. That is like a fire which is melting the permafrost. And that thawing soil, that thawing permafrost, increases microbial activity and decomposition, and as a result, carbon emissions increase. Vegetation there grows really slowly, so it's not going to recover anytime soon. Impacting the water cycle, again, it's all about the melting permafrost and the snow, increases the amount of water, so there's more water in the rivers, increased risk of flooding. In the summer, you get the ponds and lakes, so there's more evaporation. They're taking gravel where they're mining it, gravel and sand, creating artificial lakes which disrupt the drainage and leads to further melting of the permafrost. Where they build their roads, they are interrupting the drainage networks, and they're taking water from the rivers and creeks to build the ice roads that they need for the ice road truckers to come in and out with the oil, which decrease localized water storage. So we need to be able to talk about the impact of fossil fuel combustion and carbon sequestration on the flows and stores of carbon. So we have been completely dependent on fossil fuels to drive global industrialization and urbanization. And even though we're getting there with renewals, our global economy is still overwhelmingly dependent on fossil fuels. We release 10 billion tonnes of carbon into the atmosphere every year. Although when you look at the actual flows, anthropogenic or human emissions only count for, well, less than 10% of the natural flow from the biosphere and oceans into the atmosphere. It's a significant increase, and it throws the whole system into disequilibrium and impacts massively on the size of the atmosphere, ocean and biosphere carbon stores. And carbon emissions are rising faster than any time in the previous decade. Carbon sequestration. So one solution that we've looked at is carbon capture and storage, which is where you build a big dome around your power station to capture the carbon, and then you pipe it and inject it into the rocks beneath the ground where it's stored permanently. This could be an important reduction in carbon emissions. In the USA, 40% of their carbon comes from power stations, so you could reduce their emissions by 90% from power stations. However, it's extremely expensive. We had a scheme proposed in North Yorkshire, which was axed because it was just getting out of control in terms of its cost. So it's limited in its value in terms of economic and geological factors. You're going to need more than $1 billion, and you also need the geology to be right. You need porous rocks that have got impermeable rocks above them so that the gas and the carbon doesn't escape to the surface. Right, we need to be able to talk about the pathways and processes that control the short-term and then long-term changes to the cycles. So when we talk about short-term changes, we need to talk about diurnal or daily changes, and we need to talk about seasonal changes. So diurnal changes to the water cycle. At night it's much colder, so you have lower evaporation. Convectional rainfall, you need the sun to heat the land, so it happens during the day, usually in the afternoon in the rainforest, so it's concentrated then. The carbon cycle, in the daytime you've got photosynthesis taking place because the sun is out. At night, when there's no sun, you don't have any photosynthesis, but respiration is releasing carbon into the atmosphere, and the phytoplankton follow the same diurnal pattern. Seasonally, if we think about the UK, we've got a big difference in terms of our solar radiation through the year. In mid-June, we've got 800 watts per metre squared of solar energy. In December, it's only 150 watts per metre squared. So therefore, evaporation is much higher in the summer, much lower in the winter. And in the driest parts of England, up to 80% of the precipitation that falls is lost to evaporation, and river flows decrease massively. There's month-to-month variations in the amount of vegetation due to changes in the day length and the temperature. And we can also talk about the amount of foliage or leaves. So in the northern hemisphere, summer, there's a net flow of carbon from the atmosphere to the biosphere due to all the photosynthesis that's taking place. So as a result, the atmosphere's CO2 levels fall. But in the autumn and winter, all the leaves have fallen off the trees, there's far less photosynthesis, and we've got decomposition taking place. So the carbon is going back into the atmosphere, and the atmosphere carbon store is much greater. The boreal and temperate forests extract huge amount of CO2, having a really important global impact during the summer. In the oceans, the phytoplankton follows a similar pattern. When it's warmer, when there's more intense sunlight and longer day length, they will be photosynthesizing much more, and they will be taking much more carbon out of the atmosphere. And every year in the Atlantic, there's an explosion of plant life, phytoplankton, between March and summer. And you get such massive algal blooms that they can even be seen from space. And then the long-term changes to the cycles. So over the past million years, the Earth's climate's been very unstable. We've had large fluctuations in temperature. In the past 400,000 years, there have been 4 major glacial cycles. 20,000 years ago was the height of the last glacial, and temperatures were 5 degrees lower than today. Longer term, temperatures have been 7 to 8 degrees higher than today, and these climatic shifts have had a major impact on the water and carbon cycles. So the water cycle, in glacial times, there's a net transfer of water from the oceans to be stored in the ice sheets and the glaciers and the permafrost. As a result, the sea level falls 100 to 130 metres globally. The ice sheets and glaciers grow to cover 1/3 of the land surface. And as the ice sheets grow, they then destroy the forests and grasslands, so the area covered by vegetation shrinks. The climate in the tropics becomes drier, and grasslands and desert takes the place of tropical rainforest. So there's far less evaporation and far less of an exchange of water between the atmosphere and oceans, biosphere and soils, because so much water is locked up and stored as ice in the water cycle. So the water cycle is really, really slow during glacial periods. The carbon cycle, glacials lead to dramatic decrease in carbon in the atmosphere. We're not entirely sure what happens, but we think that the carbon finds its way into the deep ocean to do with changes in ocean circulation and photosynthesis, and everything that then dies goes to the bottom of the ocean where it gets locked up and stored. The carbon stored in vegetation decreases as those ice sheets wipe out the forests. The deserts increase, the tundra replaces the forests, and grass replaces the rainforest. So there's far less photosynthesis. So much is covered by ice that the carbon stored in the soil is no longer exchanged with the atmosphere. It's all locked away in that permafrost. So there's less vegetation, lower temperatures, less precipitation, less net primary productivity, and the carbon fixed in photosynthesis decreases. So again, the carbon cycle slows down massively. That carbon is stored rather than flowing around the cycle. Then we've got how human activities cause changes in the availability of water and carbon. So we need to talk about rapid population and economic growth, deforestation, urbanisation, and it's most apparent at a regional and local scale rather than on a international scale. So the human impact is clear when we look at rivers and aquifers. We are taking more water, there's increased demand for water. So places like Lake Mead in Las Vegas, the reservoir's fallen dramatically as we over-abstract water to feed a city built in a desert. So we're over-pumping that water from aquifers also in places like Bangladesh, which means the salt water gets in, which makes the water supply unfit for use for irrigation or drinking. Deforestation and urbanisation, decrease evaporation and therefore precipitation. Because you've now got impermeable surfaces, you then get more runoff and you get less infiltration. With less trees, you get less interception, and all of that water just makes its way straight into the rivers, increasing the risk of flooding. In the Amazon, deforestation has broken the precipitation evapotranspiration feedback loop, which has made the climate much drier and the forest has started to degrade. Human activities also altered the carbon cycle. So obviously we've gone in and taken those fossil fuels where they should be stored for millions of years, and we've released them and we've burnt them, and the carbon has gone into the atmosphere. So that carbon has gone from long-term storage to flowing from the atmosphere, possibly into the oceans, and making its way around the carbon cycle. So deforestation transfers 1 billion tonnes of carbon into the atmosphere every year. And that additional carbon is stored in the atmosphere and then makes its way into the oceans as well through diffusion. Even more significant is the photosynthesis by phytoplankton in the oceans. Phytoplankton absorb more than half the carbon that burning fossil fuels creates, more than the rainforests. And acidification of the oceans threatens the ocean store. Soil is also an important carbon store, and it's being degraded by humans through deforestation and agricultural mismanagement. And the carbon stored in wetlands is also impacted because we're draining the wetlands because they don't particularly look nice and we want to use the land for other things. So the impact of long-term climate change on the water cycle. We'll see increased evaporation, so more water vapour in the atmosphere. Water vapour is actually a greenhouse gas, so it helps to rise global temperatures, increase evaporation, and therefore increase precipitation. That will create increased runoff and increased flood risk. It's also water vapour a source of energy in the atmosphere, which will lead to more intense hurricanes and mid-latitude storms. Global warming will also melt the glaciers and the ice sheets like Greenland and the permafrost and the tundra, so there'll be far less water stored in the cryosphere and more water transferred to the oceans and the atmosphere. The carbon cycle. So it's quite a complex picture. So we're not just looking at increased temperature, but also geographical differences in rainfall. So increased global temperatures will lead to increased decomposition and a greater transfer of carbon from the biosphere and soil to the atmosphere. However, in the tropics, climate change may increase aridity, so dryness, and threaten the forests. If the forests get replaced by grassland, then there's far less carbon stored. In contrast, in the high latitudes, like the boreal forests of Siberia and Canada and Alaska, they will actually expand. There will be more trees able to grow in the warmer temperatures, and those extra trees will take in more CO2 via photosynthesis. The carbon in the permafrost will be released as the temperatures rise, and this will lead to acidification of the oceans as excess carbon from the atmosphere diffuses into the oceans. The phytoplankton won't be able to photosynthesize, which will limit the capacity of the oceans to store carbon. So long-term climate change will see increased carbon in the atmosphere, decreased carbon in the biosphere, and possibly decreased in the ocean. And the movement of carbon in and out of the atmosphere will vary regionally depending on the rates of photosynthesis, decomposition, and respiration. So we've got to look at global management strategies that are used to protect the carbon cycle as a regulator of the Earth's climate. So firstly, afforestation. So planting trees in areas that you've deforested, or planting trees in areas that have never had forests before. Trees take in carbon, they're a carbon sink, so it reduces the amount of carbon in the atmosphere, and the trees then store the carbon in their biomass, in their trunks, their roots, the surrounding soil. We've got several big pledges. Ethiopia have pledged to plant 20 billion trees by 2022. Pakistan have pledged 10 billion trees by 2023. However, it's not a silver bullet solution. These natural forests are often replaced with single tree forest, so the biodiversity is not there. And often non-native species are planted, which creates ecological havoc. In 2019, Turkey set a new world record for planting 11 million saplings, baby trees, in 3 hours. However, a few weeks later it was reported that 90% of them were dead. A quarter of all saplings planted die, and it actually takes 20 to 30 years of growth before a tree effectively takes in significant carbon. And to combat the disequilibrium in the carbon cycle, we would need to plant trees 5 times the size of India. And that would have disastrous consequences on food security because we wouldn't have enough land to grow crops. Then you've got greenwashing. So this is where bands like Coldplay say they'll plant a tree for every ticket sold to their new tour. However, this is a way for polluters to ignore real emission cuts, takes the focus away from emission cuts. And whilst emissions remain as high as they do, the impact of tree planting is limited. The second strategy is wetland restoration on a global scale. So restoring the salt marshes, peat bogs and mangroves, because they store 35% of terrestrial carbon. We've got schemes in Cambridgeshire, we've got schemes in Canada where they are restoring their wetlands by bringing the water table back to the surface. However, the wetlands only occupy 6 to 9% of the Earth's surface. They do a great job of taking in and storing carbon in their anaerobic conditions, but even when they're fully restored, this will have limited impact on a global scale. Improving agricultural practices includes not ploughing, so you don't turn over the soil and lead to oxidation, putting the crop residue back onto the fields, the leaves and stems, to encourage decomposition, using new varieties of rice that will produce fewer emissions, and looking at your feed for your livestock, so to try to reduce the amount of methane they produce, putting garlic into their feed. However, that leads to garlic flavoured milk, which hasn't gone down well. Storing their manure in anaerobic containers, capturing the methane from that, and then using it as renewable energy. And then you've got reducing emissions through international agreements. So it's been quite patchy international cooperation and success. It all started with the Kyoto Protocol in 1997, where all industrialised countries were set targets to reduce their emissions. However, America, who was obviously a major emitter, refused to sign, not wanting a negative impact on their economy. China and India were not set targets because they were not seen as industrialised at the time and went on to become 2 huge emitters. The targets have been voluntary and not legally binding, and some countries have met their targets and made progress, and some haven't, with no real consequences. We've got the Paris Climate Change Agreement, which was reached in 2015, came into force in 2020, with the aim to reduce carbon emissions below 60% of 2010 levels by 2050 and keep global warming below 2 degrees. It's had some success so far. America came out of it when Trump was in charge, saying, "I represent Pittsburgh, not Paris." But however, on his first day in office, Biden rejoined the agreement, which is good news. And we wait to see how successful that will be as countries are setting their own targets. Countries like China and India have set targets where they will peak their emissions in 20 to 30 years' time. So they're still planning on increasing their emissions to a point before they then look to reduce them. You've also got the carbon trading scheme, or the cap and trade scheme. This is where a cap is set in terms of the total emission space available, and businesses can trade their emission space with one another, but you're controlling the total amount of emissions. The idea is that you lower the cap over time to reduce total emissions. However, after a decade, the European scheme has brought little reduction in emissions. There's a perceived risk that caps on EU emissions will price businesses out of Europe and into less regulated markets. So that is all the content for Earth's life support systems. And then remember, you just need to look at some skills. You need to be able to read a climate graph. Remember that the bars show the rainfall, the average taken across 30 years for each month for that particular place. And the red line shows the temperature. Again, the average taken over 30 years. So there are some limitations to that, in that you've got a 30-year average, and things might have changed quite significantly in the last 5 years or so, but the average doesn't really show that yet. You also need to be able to calculate a simple mass balance. So this is where you would add up all of the inputs and add up all of the outputs and take the outputs away from the inputs. If you have a positive number, you've got a positive balance. If you have a negative number, you've got a negative balance. If it's 0, it's completely balanced and in equilibrium. The other thing that you might be asked to do is to look at rates of flow on a graph, or you might also be asked to convert some units, maybe from gigatons to tons. Okay, so I hope that is helpful to you. I realise that I have talked for 1 hour and 40 minutes, so I hope you've not fallen asleep and that you've made it to the end of this revision video and that it's been helpful. So all that's left to say is good luck in your exam. Let me know if you need any help with anything.